The purpose of this talk is to prepare the non-experts for a meeting that's going to be happening, I guess, in the end of this month here on connection between metric embeddings and geometry. And this meeting is actually devoted to new directions in the theory. And what I want to do is just explain some of the old results or some of the ways of looking at some of the questions. And there is no way I'm going to do justice to even 1% of this theory. But I'm gonna give a talk which explains the background and shows how we think or how we approach all kinds of questions from this type. I'm gonna definitely, I don't want to be encyclopedic. I don't want to list a whole list of results. There are surveys online which are non-technical and just list a huge shopping list of beautiful applications of this theory. I'm gonna give some of them, but I refer you to those surveys. But I'm going to emphasize ideas, so I'm going to be proving a few theorems with full details. And this is really for the non-experts. So one of the things I can promise is that you're not going to see a proof from after 1985 in this talk. Okay, so this is old mathematics, but all the ideas that we're doing, what we're discussing here, are really what is going to be used and discussed a lot in the conference. So we're going to be discussing metric spaces. So for those of you, so I guess it's an abstract set with function D. And I'll just write once in this talk. We satisfy the triangle inequality. And it's symmetric. And I guess this final condition, which will not matter much to us. And what we're going to be trying to do is we're going to be we'll be trying to understand such geometric objects in relations to other geometric objects. So we are going to be usually assuming that we have some given metric space X, let's say with a metric corresponding to X, and Y with a metric corresponding to Y. And we're gonna be studying these objects in a relative way. We're gonna be asking ourselves, how compatible is the geometry of X with the geometry of Y, and what does this tell us? Okay. So such questions occur all over the place in mathematics. We will see many examples in computer science. They occur in roughly two types of ways, very, very roughly. One of them is when we actually ask a question about a metric. So we will see many examples where just the question, the algorithmic tasks that we ask about are about metric spaces. So clearly we're going to be studying metric spaces. And we're going to see an example of situations where we introduce an artificial metric, apparently artificial metric, to a problem in order to solve it, even though the problem a priori had no metric in it at all. So these are two types of approaches. One of them is questions about metric spaces, and the other one's using geometry to solve combinatorial optimization problems which seem to be non-geometric, but as we will see, they actually are. But okay, so before we discuss some theorems and concepts, let me give a whole list of examples. So the world of metric spaces is large and complicated, and so I want to give a few lists of things of metric spaces that we will care about, and then when we're going to be stating theorems in complete generality about arbitrary metric spaces, you keep in mind that we're somehow handling all of these things at once. Okay, so these are usually quite strong theorems, but of course, so for people that are, for I guess most people here, the first example would be graph metrics. So shortest path metrics and weighted graphs. So I wrote many things. I guess, for those of you who were in the morning session, word metrics and groups we're gonna be seeing, which are of course a particular case. Or as Avi called it, the Gauss functional whatever. That's so Riemannian manifold. And towards the end, we'll be discussing something called sub-Riemannian manifolds. So that's later for those of you who don't know what this concept is. Normed spaces. And then there are all kinds of objects which are specific metric spaces, but we really understand them unsatisfactorily. So there is, just as an example, there is a metric called edit distance, which is the following. So I guess it's a metric on the space of all infinite strings of zeros and ones. So let x be all the finite strings but unbounded length. So x is all the finite strings of, let's say, 0, 1. Plays no role here if it's another alphabet. And then it is a graph metric, so I'll tell you when two strings are neighbors. Two strings are neighbors if, so this is some whatever, and there is another one here. Two strings are neighbors if you can reach from one to the other by either inserting a 0 and a 1 wherever you want, or deleting a 0 and a 1. Okay, so that's edit distance. There are going to be various variants of it, and we understand them very poorly. So there are something called earth mover metrics, or transportation cost. And so let's say in the simplest case, in the plane, we were gonna, so for example, we can look at X to be all the set of all endpoint subsets of the plane. And the distance between two sets is the infimum. So here is one. This is A. They can overlap. It's B. I should have used more colors. And we look at all the ways to match a point to A to a point to B, such that we minimize. Well, there are many functionals we can minimize. Here is one example. And this is the infimum over all functions from A to B, which are one-to-one. Okay, and there are very fuzzy versions of this, which are distances between measures, which probably we won't get to. Then there are objects of the like metric transforms. So if you start with an arbitrary metric space, and if you have a function omega from 0 infinity to 0 infinity, which is concave, increasing, and 0 at 0, then omega at dxy is also a metric. Okay, and so this is also a metric, easy exercise. But this is a way to start with simple objects and create more complicated ones, and we're going to be using them. We're going to be seeing how they appear naturally in algorithmic contexts. So a simplest case, which is when omega of t is t to the alpha for some alpha in 0, 1, that's called an alpha snowflake. And we'll get back to it, of the original metric. And okay, some more operations which we will be using a lot are notions of quotients. So these are roughly, I'll get to it when we need it, are, yeah.
You may want to write a little bit bigger because of the videotaping.
It doesn't come out? Are you sure? Okay, all right.
The black there. I get you more colors.
There is black and there is red.
Yeah, I know.
So, so for those of you who are watching the movie and are seeing, so we're discussing metric spaces, and and quotients are ways you start with a metric space and you obtain a new metric space by identifying points. So, okay, so there is some, so it's not only identifying points, but and constructing an appropriate metric. We'll get to it when we need it. So quotients and snowflakes and subsets make this world extremely rich. Final example. So here, it's a metric that's coming up in things that I'm recently doing. I don't think we'll get to it in this talk. You can look for, so here's an example of a metric space. Look at all, let's say, all the subsets of the integer grid, which are finite. So here's the integer grid in the plane. And we have some subsets. This is one of them, and let's say this one, some points are common, some points are not. And let's say this is 0. So the distance between two subsets I define is the shortest traveling salesman tour, the traveling salesman tour, which starts at 0, visits the symmetric difference of the sets, and comes back to 0. Okay, so those of you who've seen this object know this is related to something called the Lamplighter group, and these are also metrics that all of these are going to be coming up in, first of all, in problems that we want to address, and all of our theorems are going to be applied to this rich world of metric spaces. So this is rich and complicated, and what we're going to be interested in are embedding questions. So embedding problems. So very roughly speaking, we have two metric spaces, x, dx. We think of x as small. Y, dy is, okay, so y is going to be large. And the goal is to represent x as a subset of y while preserving some geometric information. And this interpretation of what does it mean to preserve the geometric information has dozens of interpretations, and we really, these dozens of notions of faithfulness of embeddings come up in applications. So we're going to be discussing probably three different kinds of notions of preservation of information, but this is but I'm being vague because there are many, many, many ways to interpret this. Okay, this is so the simplest example would be so the simplest example would be by Lipschitz embeddings. And that's it's really the simplest. So what you want to do is you want to look at, you take a function f from x to y, and you look in the image at the distance between 2 points. You want this to be at least alpha, the original distance, and at most beta times the original distance. So we want the distances to be computed in this way, and we will denote, so the distortion, or the best distortion, the distortion of x in y is the infimum over beta over alpha over all such f. All these embeddings between x and y. You might ask, why are we looking at the ratio? There are many good reasons. This is really the right notion to look at in many contexts. But the obvious answer would be that this makes it scale invariant. So we're going to be really identifying two metric spaces which are just such that the metric is a multiple. One metric is a multiple of another. So take the distances multiplied by 10. This is the same metric space. So saying that so the distortion will denote it by c sub y of x. So just to get used to it, what does it mean that c sub y of x is at most some number d? This is the same as saying, or strictly less than d. Well, this is the same as saying that there exists a function f from x to y and a scaling factor. This is, let's say, lambda, such that for every 2 points, the distance in y from f of a and f of b is at least lambda times the distance in x from a to b, and at most d times the distance in lambda times the distance in x from a to b. So up to rescaling the metric, you get the right answer after embedding up to this factor d. Okay, so sometimes I will write, this is just notation, when I write this, I mean that. Okay? No. Here, so lambda is our alpha, and then beta over alpha is going to be d. So you need d time. So before I start proving some theorems, why do we want to embed? So these kind of this natural question occurred probably first time almost a century ago in mathematics. And actually, and of course, and let's say roughly a decade ago, a lot of applications to computer science started emerging, and there are several reasons. So first of all, so when you look at this situation, you can think of Y as a space that you think you understand. Okay? Maybe we know what's going on in Y. We believe we know that what's going on, that we understand Y. So if we understand Y, then an embedding is telling us something about the structure of X. And I really want to emphasize this. So embedding is just a slick way, usually, to really say that you understood something. Yes. Yeah, but all of the theorems, and you're going to see, people say something embeds into something else. That's a very quick way of saying I understood something about X. I looked at X, I understood what's going on there, because the embedding itself involves some structural information, some structure, something that you understood about X. So we are really interested.
X into what?
Yeah, what do you say? I'm in the same situation always.
So if you prove that something does not embed in something else, it means that you didn't understand.
Okay, so that's why there is a 1 here. So actually, and this is a direction which is more common in analysis, even though I know one such example in computer science. But so embedding problems of X into Y, embedding problems, or computing Cx of Y, Cy of X, so the embedding of X into Y tells us something also about Y. So, like Noga said, and this is the way this is really used most often in analysis, is saying that Y, something about Y, doesn't allow X to be embedded in it, or X from a certain family, is a structural information on Y. Okay, there is something about the geometry of Y which doesn't allow certain X's inside. And this goes really the opposite direction than the way things are used in computer science, except for one example, which I will get to in the end, which was actually used in this way. So we embedded things into a combinatorial object in order to say something about the big object. Okay, but this is actually most of the mathematical applications go through direction 2.
So going to restrict to a family of functions, so any kind of function. So we cannot restrict to a particular family of functions.
What do you mean?
Say, for example, in that, if you move over from a particular set of functions.
Sure. Yeah. I mean, so. Yeah, if you have some special, well, you need some more at this level of generality. I don't know what you mean by special family of functions. For linear spaces, you might be interested in linear mappings, or for groups, you might be interested in equivariant embeddings or things of that form. And then we're definitely interested in these questions. And some of the basic theorems are that you can actually prove that for certain classes of groups or certain classes of normed spaces, the general question reduces to the special family of functions. So reducing how large the set of possible embeddings can be is actually a meaningful research direction. And there are, but you need more structure. Well, we didn't arrive there yet. Okay. Yeah. Yeah, this is so it's very nice that everybody's preempting my next item. we're here to solve problems. And so I guess this belongs to one, but it's of a different kind of, it's of a different nature if we understand why, or maybe we're used to why. Okay? We've been playing around in Y for years and years, and we know how to build sandcastles in Y. Then when we embed X into Y, we can do things to X which would have seemed perverse without the embedding. Okay, so embedding something into Hilbert space, and then afterwards looking at the image and projecting it or separating it with hyperplanes or things of that form, and the original space, if the space was a graph, that would look quite crazy, while it would be extremely natural on the target space Y. So solving problems, in mathematics, this is done a lot in group theory. We prove algebraic properties of groups by first representing them in some subspace of some natural space, and then just deducing something about their algebraic structure from these embeddings. And in computer science, there are many problems, so there are many problems, and we will see them, can be solved efficiently, say, in Hilbert space. And then an embedding would imply embedding would allow us to use our black box tools for X. Okay, so would allow us to transfer these methods. So I'm being vague, but we'll see. To X, and as Avi said, the minute you look at the second item here, then you have another burden, which is you want to be able to compute your embedding efficiently. So what I'm going to show you is and I really think, I don't know of a single example of an embedding theorem which isn't efficient. So the nature of this field is that when...
Random is not...
Oh, if you allow randomness, but okay. So if I...
It's either random or efficient.
Well, even I don't think I know of an example of an embedding theorem which cannot be de-randomized. Yeah, so I really think this is the nature of the field. Even though it seems like an issue, it's never an issue. Okay? And I would be really happy to see an embedding theorem for which there is even a little difficulty of making it efficient.
There are embeddings of L1 and L2 by linear mapping, which are not known.
Yes. Okay. So I'm allowing randomness. Yeah, I'm allowing randomness. Okay. But if you allow randomness, then these things are constructive by nature, because this is probably the nature of the people who've been working in these fields till now.
But even there, I think if you allow some distortion, it shouldn't matter, right? Whether you have
No, because if you want to get the optimal, if you care about dimension, not the optimal dimension, then you know there are all kinds.
Optimal dimension or
exact. Yeah. Okay. If you're willing to lose something in the dimension, or then you can do it. But yeah, there are situations that you can come up. But if I allow randomness, I really don't know of an example of an embedding theorem which wasn't efficient. So, and actually, I thought about it. I think it's a challenge to somehow come up with something which isn't efficient. This is maybe my weakness as the way I think, but I cannot come up with proofs like this, okay, of embedding theorems. Yeah.
An example where there exists an embedding, but the random embedding is not good.
So, I mean, I don't know how you define random. Most of these
a small number of good embeddings, but most embeddings are really bad.
I still don't know what you mean. I mean, in this context of generality, I mean, there is no natural notion of randomness in any of these objects.
I think maybe usually only in dimension reduction things, then random pop up. In many examples of embedding, random is not particularly good, no?
Okay, I think the discussion on random doesn't belong here right now. Okay, we can discuss this later. I really don't think it belongs here at this point. Okay, you will see examples of embeddings and
Every
yeah.
metric is isometrically embeddable in L infinity. A random one will definitely not give it.
Yeah, we'll prove this in a second. But okay, so let's get to some mathematics. Okay. Okay. Okay, maybe I should say before that at least when it comes to embedding into Hilbert space, so if Y is Hilbert space, then really this is just a theorem that there is a polynomial time algorithm, and let's say X is finite. So then the embedding into Hilbert space of X, the best distortion can be computed with arbitrarily good precision in polynomial time. And the optimal embedding can also be computed in polynomial time. So you're really studying the number and the algorithm is automatic. Okay? And this is just because this is an obvious semi-definite program. So I mean, in the case of Hilbert space, what you want is you want to find, so assume that your original metric, it's finite. So we can think of it as the numbers 1 to n with symmetric. And then what do I want? I want to find vectors, x1 up to xn, in Rn, such that the distance from xi to xj, I'll square it, is at least the distance from I to j squared, and at most, call this thing d squared, the distance from I to j squared. So if you call Aij the Gram matrix, then this is just linear inequalities. Aii plus Ajj minus 2Aij. These are linear inequalities on the semi-definite, positive semi-definite matrix. So finding the best you can do in polynomial time. So there is no issue of computation. These are really questions about understanding the geometry. Okay? These problems come automatically with an algorithm. Okay? In other spaces, this is not true anymore, but still, it's Aij is the Gram matrix.
So we are fixing x and y, and we are trying to find the best possible distortion, right?
Yeah, so we would like to minimize this such that there exists a matrix, a positive semi-definite Aij, satisfying these inequalities.
Is the reverse problem is also efficient?
Reverse?
Say we have x and some distortion around, and we want to find the best possible y that is conditioned.
To find the best possible y, I don't.
Yeah,
Why would it just x?
Based on the what?
On some assumptions. Oh, let's continue with that. I think more about this.
Okay. Later we're going to be looking at embeddings into L1 where this is not true anymore, but still all the proofs are constructive because at least they've been so far. Okay, even though there are computational issues. So I really don't believe that's an issue. I mean, I really think these are problems understanding geometric structures. So what I'm going to do now is I want to, okay, so maybe Noga mentioned this, so there is a trivial embedding theorem, L infinity. So if X is a metric space, you can always assume that X is finite in this talk. Then we can send a point, so we can define f of X. So we can look at R 2 to the x. 2 to the x is the set of all subsets of x with the L infinity norm, the maximum of the coordinates. And we can define function f from x to r 2 to the x by f of a point x with index. So now the coordinates are indexed by subsets. It's just the distance from x to the subset. And then an easy exercise is to show that that fx minus fy L infinity, which is just the maximum of the distance from x to a and the distance from y to a over all subsets, equals the distance from x to y. So this is an isometric embedding always. Okay, so that's the simplest possible situation. Everything is a subset of L infinity. Okay. Yeah, you're right. You're right. You're right. In this setting, it's enough to take the points. But yeah, you're right. You're right. It's so yeah, we can also later we'll so we can just take Rx. So f of x at the coordinate y is the distance from x to y works just as well. But we will very quickly need to look at sets. Okay. So what I'm going to be doing now is I'm going to be proving two of the people in analysis have been studying these kinds of questions since the 60s. But in 1979 and then in 1984, there were two major paradigm shifts in this field. There are two theorems that changed the way we look at it, and everything that we do today are variants, or we're building on these insights. So there's something called Aswad's theorem. From 1979, and Bourgain's theorem. 1985, they are really major paradigm shifts in this theory, and I'm going to prove these theorems in full detail for two reasons. First of all, in them are you really need to know these two theorems to understand the way people think today. What people are doing today in proving positive embedding results is really, just sophisticated versions of the ideas that were here. And second, so there are all kinds of notions that will come up in the conference, like, multi-scale analysis, or all kinds of buzzwords, and you'll know what we mean after we see these proofs. Okay, so these are two very important theorems. Of course, I say they're paradigm shifts. Neither of them occurred in a vacuum. Aswad's theorem is the construction, and I mean the ideas are very related to what has been done in real harmonic analysis at the time. And Bourgain's theorem is well, I think that's more out of the blue, but it's very close to things that people have been looking at in the local theory of Banach spaces, which Bourgain was working on at the time then. But let me start with Aswad's theorem, and I really want to just prove them now. Okay, so Aswad's theorem is the following. So before that, there is this, so there is a way, we need to quantify what is the dimension of a metric space, or bounds in the dimension. So this is the basic definition. I think it was called doubling in the early 70s. Originally in the harmonic analysis literature, the condition I'm about to write now is what's called homogeneous spaces. So So a metric space is called doubling if there exists some constant, lambda. In all the literature at the time, it was usually written 2 to the kappa. You need to think of this kappa as the dimension of the space. If there is some number lambda, such that for every x in x and for every radius r, if I look at the ball, I should say that the ball around x of radius r is the points, all the points y and x whose distance from x, balls are going to be closed in this talk, less or equal to r. So such that for every r bigger than 0, the ball around x of radius r is inside the union of so lambda is an integer for some So the picture is that I have my metric space, and inside there is a point, an arbitrary point, and an arbitrary radius, and I look at the ball around it, and no matter how I choose in this arbitrary point and this arbitrary radius, I will always manage to cover it by finitely many balls, boundedly many balls of half the radius. Okay, so the obvious example, and this is why people write this as 2 to the kappa. No, well, it's clearly related, but it's other dimension. It's a number associated to a metric space which you should think of as a bounded dimension. I'll tell you exactly. Actually, this issue is making this thing continuous. It started as you know, as a bounded dimension. There were questions of how can you turn this into a dimension. That was the reason Aswad looked into this, turning the discrete thing into a continuous problem. But that's somehow the opposite direction.
So the thing is that it's like kappa doubling, like the parameter of the space is kappa?
Usually, it depends who you ask. Okay, so I'm used to lambda just because in the textbooks that I looked, it was called lambda. And in Riemannian geometry, people usually write 2 to the kappa. It doesn't really matter. So the obvious example is you can look at Rn or Rd with any norm. And then we know that what is a ball? So if the ball around x of radius r, we know that its volume is, well, it scales like r to the d times the volume of a ball of radius 1, around 0. And therefore, just by the usual covering argument, or packing and covering, you get that in this case, r to the d with a norm is doubling. With constant, I guess, 2 to the d. Let's say 4 to the d. Okay, so that's just because you just take. Did anybody ever not see this? Is there somebody who hasn't seen this computation? Okay, so what you do is you look at so you take a ball of x in a radius r, and you look at so this is r, and you look at a maximal r over let's say r over 2, r over 2, I guess. Separated subset. Do I want r over 2? Okay, yeah. So this is so I'm going to take a set of points. So I'm going to take yi, I goes from 1 to capital N inside this ball around x of radius r, which are such that yi minus yj is at least r over 2 for every I and j, and you take a maximal, and this is maximal. So because it's maximal, if you draw a ball of radius r over 2 around them, then the union of these balls will cover everything, and I guess if you want to lose a lot, the balls of radius r over 4 are disjoint. So the balls of radius y, these balls are disjoint, and contained in and contained in the ball around x of radius 5 r over 4, right? So it's 5, whatever, yeah. Okay, some constant. So, but we know that so these are disjoint, so the measure of this must be at least the measure of this, and the measure of, these are disjoint, so we get that n times r over 4 to the d times this, give it a name, v, times v must be at most 5 over 4 r to the d v, so the number of balls is 5 to the d, at most 5 to the d. That covered it. Okay? And
is every metric space doubling for some constant?
no. No.
Metric spaces which are doubling?
Yeah. No, take infinite dimensional Hilbert space. So infinite dimensional Hilbert space, you just take an infinite set of points, the distance between any two is 1. So how many, so look, this is one big ball of radius 1, but you need infinitely many balls of radius a half to cover it. Okay, so, so if you think about this, that's a nice exercise. It's a little twist on this argument. So if I have a metric space x and d, and it has a measure on it, mu is a measure, finite measure on x, that doesn't have to be finite, such that the measure of a ball around x of radius 2r is at most some constant times the measure of a ball around x of radius r, then it's doubling. And this is for every x and for every r. Then xd is doubling. With constant lambda, which depends only on dc. Okay, so you need to reverse this argument, except that now you don't know that all of these balls have the same measure. So you have to think a little bit. Okay, but that was it. And I should have said here that so this is equivalent. So the reverse direction is also true. That's a non-trivial fact. It's due to Volberg and Konyagin. That if a space is doubling in this combinatorial sense, then you can construct a measure which satisfies that inequality. And then relations are almost, they're not really optimal, what's known, but very close to being optimal between the C and the lambda. It's a Borel measure. Think of finite metric spaces for now, but.
Oh, so just finite.
Yeah, no, but otherwise all you need is.
It's always for some constant.
As a function of the dimension. No, but I want to find the
lambda of C.
Okay, so it's going to be lambda of C is going to be some power of C, and here the C is going to be a power of lambda Okay, so there is, and the power is at 1 plus epsilon, I think.
Doesn't depend on mu at all?
What depends on mu?
The lambda?
No, just a function. This is the same proof. There's a, okay, so do the same thing, and there is this issue I said that all these small balls don't have the same volume, the same measure mu, so think about it. In the end, I'll show you how to do it if you don't see. But, so this is the same thing. So being doubling just means that there is a notion of volume which behaves like Euclidean space, like fine-dimensional Euclidean space.
So do you only take this theorem for finite spaces with the counting measure?
Okay, you want to, the condition of Wahlberg is so okay. So I think you know the answer. So so the theorem of Wahlberg and Konyagian is that if your metric space is complete and it's combinatorially doubling with constant lambda, then you can find a Borel measure on X, which is non-trivial. Every ball is sent to a strictly positive number, and it satisfies the inequality up there with constant C, and C is at most lambda to the power 1 plus epsilon. And for
This is the reverse.
the reverse, you need completeness, okay? But and actually there are counterexamples in non-complete spaces, but we're not. This is not really the topic, okay?
The other statement, so that if you have a measure, then this implies a doubling. So what do you assume about the
Again, the measure. All I need is that every ball is measurable and no ball is sent to has measure 0. Okay. I'll show you the proof in the end if you want, okay? It is just a digression. Okay, so a Swad's theorem is that if xd is doubling with constant lambda, and epsilon is, then for every epsilon bigger than 0, let's say in the interval 0, 1, there exists a distortion which depends only on these numbers, and a dimension which k, which depends only on these numbers, such that if you take the metric and raise it to the power 1 minus epsilon, then this embeds with distortion this d into r k. Okay? So if you don't mind losing this epsilon power, this snowflake operation in the metric, then you are really in low dimensional space. Obviously, if you have such an embedding, then you inherit a measure, you can just pull it back. So obviously, if you have such an embedding, the power here doesn't matter at all. It just changes the constant there. Such an embedding implies that the space is doubling, but amazingly, the reverse direction is correct too. Okay, so this is an example where we start with an arbitrary metric space and we get an embedding. And I really want you to see what is happening here, because the ideas here are very important for modern embedding theory. But you might be wondering, what is this 1 minus epsilon business? So Pansu proved that taking the snowflake, so raising the metric, the d to the 1 minus epsilon is operation is necessary. And I will not say more. But we really need this. It's not true that you need to change the metric a little bit. It doesn't ruin much, but.
Does it prove that you actually have to take a polynomial, or could it be just a little lower? Could it be
what will the proof give? Oh no! It will give you can d over some power of log. What you will get from the proof. The proof you will see. You will see exactly where the power comes up, and you will see that you can d over log d, or maybe d over log d squared or something like that.
Enough for the embedding.
Yeah.
I just last thought k is a polynomial in 1 over epsilon 1 over.
It depends on the data. Think of lambda is 100 and epsilon is 1 over 100. So they're constant. So there is a distortion and there is a dimension. Okay?
The dimension k of lambda epsilon for constant epsilon is going to be roughly log of lambda, but if lambda is 2 to the k.
For constant.
This is roughly the dimension you expect.
Yes, so that's going to be, yes, so roughly we mean up to powers 1. No, there are more logarithmic terms and things of that form. Yes, you will see this is a...
What do you expect from the doubling definition?
Close, but we don't know exactly the complete answer yet. I mean, you will see from the proof there is what I'm going to show you is going to be wasteful, but there are really like natural ways to tighten it, and if you want to really tighten it, you have to do it very more delicately. But you know this is but you see the proof, and then you'll get the answers. Okay, so let's see so proof of a Swad's theorem. So what does a SWAT do? Okay. So let's fix some number c bigger than 0. And let's say script n in my metric space be, I guess I did here a CNet. Be a CNet in the space. So by that I mean the union of the balls of radius c in the set is all of x, and if z and z prime are in this net, then their distance is at least c. Okay, so you can do this by taking a maximal C-separated subset of the set, of the space. Okay, so you take such a net and you define a graph structure on N. By the way, what I'm showing here is verbatim Aswad's proof. Okay, this is identical to what's in his paper. I should have said that the reason Aswad was interested in this question is exactly related to the questions you asked. So in the 50s and 60s, people have been just assuming that spaces are doubling, but you know, there are all kinds of arbitrary parts of this definition. What is the ratio? What is important about dividing the radius by 2? Why not by 4? Why do you want the dimension to be 2 to the kappa and not 3 to the kappa? There's a lot of arbitrariness. So because of all these choices, he found a way to turn this into a meaningful notion of dimension, to turn the discrete thing into a continuous thing. But along the way, he discovered this theorem, which is of a much more lasting impact than his dimension theory, okay, in my opinion. But there are all kinds of arbitrariness here, which you have to overcome if you want to really turn this into a dimension theory, which is really relevant.
You could define dimension by the smallest dimension of RK such that it embeds into small distortion.
But then there's this raising to the power 1 minus epsilon issue. There's a lot of choices, a lot of parameters. You have to write the quantifiers correctly. You know, you have to think a little bit before you do that. But this theorem, you have to think a lot before you discover it. You have to believe that it's true. Okay, so we define a graph structure, which analyzing these graphs is what we do all the time in